Albert Einstein wrote a letter in 1935. It was not a personal letter. It was not a note to a friend or a request for a job or a complaint about the weather. It was a scientific paper published in a respected journal, co-authored with two colleagues named Boris Podolsky and Nathan Rosen. The physics community calls it the EPR paper after the initials of the three authors. In this paper, Einstein made an argument, a careful, logical, devastating argument designed to prove that quantum mechanics was incomplete, that the theory physicists were using to describe atoms and electrons and light, the theory that was making perfect predictions in every experiment, that this theory was missing something, that it could not possibly be the whole story. Einstein was not attacking some fringe idea. He was attacking the most successful theory in the history of science. Quantum mechanics predicted the behavior of atoms to 10 decimal places. It explained the periodic table. It explained why metals conduct electricity. It explained the colors of flames and the structure of molecules and the stability of matter itself. And Einstein said it was wrong, not wrong in its predictions. The predictions were fine, wrong in its description of reality, wrong in what it said about how the universe actually works. The physics community split. Some sided with Einstein. Some sided with the quantum physicists in Copenhagen, led by Niels Bohr, who defended the theory. For decades, the debate raged. Conferences were held, papers were written, insults were exchanged. The greatest minds of the 20th century argued about what Einstein's letter really meant. I read that paper when I was young. I read it carefully. I read the arguments, the equations, the philosophical conclusions, and I thought it was nonsense, not because Einstein was stupid. Einstein was a genius. Einstein changed the world. Einstein understood things about space and time and gravity that nobody had ever understood before. But on this particular question, on this particular argument, Einstein was wrong. Not just wrong in his conclusion, wrong in his reasoning, wrong in a way that reveals something profound about how even the greatest minds can be fooled by their own intuitions. Let me show you what Einstein argued. Let me show you why it seemed so compelling. And let me show you why the universe proved him wrong in the most spectacular way possible. The argument goes like this. Imagine you have two particles. They are created together in a special way, a way that links their properties. We say they are entangled, though Einstein did not use that word. He hated that word. These two particles fly apart. One goes to the left, one goes to the right. They travel for miles, for light years, for any distance you like. They do not interact with anything. They do not communicate. They are completely isolated from each other. Now you measure something about the particle on the left. Say you measure its spin. Is it spinning up or spinning down? Before you measure, quantum mechanics says the particle does not have a definite spin. It is in a superposition, a blur of possibilities, both up and down at the same time. But when you measure, you get a result. You find the spin is up. Here is the strange part. The moment you measure the left particle and find its spin is up, you instantly know that the right particle has spin down. Not because you measured it. You did not touch it. It is miles away. But because of the entanglement, because of how the particles were created, their spins are correlated. If one is up, the other must be down. This bothered Einstein deeply. How does the right particle know what you did to the left particle? How does it know to be spin down the instant you measured spin up on the other side? The measurement happened just now. The information would have to travel from the left particle to the right particle, but the particles are miles apart. The information would have to travel faster than light, and nothing travels faster than light. Einstein called this spooky action at a distance. He meant it as an insult. He meant it to show that quantum mechanics led to absurd conclusions. If the theory requires instant communication across arbitrary distances, the theory must be wrong. His solution was simple. The particles must have had definite spins all along, before you measured, before they separated. From the very moment they were created, the left particle was spin up and the right particle was spin down. They carried these values with them like cards in sealed envelopes. When you measured the left particle, you were not creating the result. You were revealing a result that was already there. Quantum mechanics said the spin was undetermined until measurement. Einstein said that was ridiculous. The spin was always determined. We just did not know what it was. The theory was incomplete because it failed to describe these hidden values, these hidden variables. If Einstein was right, quantum mechanics was not a complete description of reality. It was a useful tool, a statistical approximation, but underneath it there was a deeper layer, a layer where particles had definite properties at all times, not this fuzzy superposition business, not this measurement creates reality mysticism. That was the argument, that was the letter, that was what Einstein believed until the day he died in 1955. And I am going to tell you why he was wrong. For 30 years, nobody could settle the argument. Einstein said there were hidden variables. Bohr said there were not. They argued in conferences. They argued in letters. They argued over dinner. Neither could prove the other wrong because both positions seemed logically consistent. It was philosophy disguised as physics. You could believe whatever you wanted. And then in 1964, a physicist named John Bell did something remarkable. He found a way to test the question experimentally. He turned philosophy into physics. Bell was a quiet man. He worked at CERN, the particle physics laboratory in Switzerland. He was not famous. He was not part of the great debates. He was just a careful thinker who noticed something that everyone else had missed. He noticed that Einstein's hidden variables theory and quantum mechanics made different predictions, not in ordinary situations. In ordinary situations, both theories predicted the same results. That was why the argument had raged for so long. You could not tell them apart with simple experiments. But Bell found special situations, unusual measurements, specific angles and correlations that would give different numbers depending on which theory was right. He derived an inequality, a mathematical limit that any hidden variables theory must obey. If the experiments violated that limit, Einstein was wrong. If the experiments respected that limit, quantum mechanics was wrong. It was a beautiful piece of work. A simple, elegant test that could finally answer the question that had haunted physics for 3 decades. And then we ran the experiments. The first serious tests came in the 1970s and 1980s. A French physicist named Alain Aspect built increasingly sophisticated experiments. He separated particles by meters, then by kilometers. He changed the measurement settings while the particles were in flight, so fast that no signal traveling at the speed of light could carry information between them. The results were clear. Bell's inequality was violated. Quantum mechanics won. Einstein lost. The particles did not carry hidden values with them. The spins were not determined in advance. The measurement on one side really did affect what you could know about the other side instantly across any distance. Spooky action at a distance was real. Now let me tell you why I said Einstein's argument was nonsense. Because it was not just wrong, it was wrong in a subtle and instructive way. It was wrong because Einstein could not let go of a picture of reality that seemed obviously true but was not. Einstein believed in local realism. Local means that things are affected only by their immediate surroundings. If I push a ball, the ball moves because I touched it. If I want to affect something far away, I have to send a signal. I have to wait for that signal to travel. Nothing happens instantly at a distance. Realism means that things have definite properties whether or not you look at them. The moon exists even when no one is watching. The electron has a position even when no one measures it. The universe is out there, solid and real, independent of our observations. Both of these seem obviously true. Both of these match our everyday experience. Both of these are deeply intuitive assumptions that humans have made for thousands of years, and quantum mechanics violates them. Not one of them, not local or realism separately. The experiments show that you cannot have both. You can have a universe that is local but not realistic. You can have a universe that is realistic but not local. But you cannot have a universe that is both local and realistic. The mathematics forbids it. The experiments confirm it. Einstein could not accept this. He could not imagine a universe where the moon does not exist when no one is looking. He could not stomach a universe where measurement creates reality rather than revealing it. So he invented hidden variables. He tried to restore the solid, common-sense picture of a universe that exists independently of observation. But the universe does not care about our comfort. The universe does not care about our intuitions. The universe does what it does, and our job is to figure out what that is, not to tell it what it should be. This is where Einstein went wrong, not in his mathematics. His mathematics was fine, not in his logic. His logic was impeccable. He went wrong in his assumptions. He assumed that local realism must be true. He assumed it so deeply that he never questioned it. And when he built an argument on that foundation, the argument was doomed from the start. I want to be careful here. I am not saying Einstein was foolish. Einstein was anything but foolish. I am saying that even the greatest genius can be trapped by assumptions that seem too obvious to question. Einstein revolutionized physics by questioning things that everyone took for granted. He questioned absolute time. He questioned absolute space. He questioned the idea that gravity was a force. He tore down assumptions that had stood for centuries and built new structures in their place. But he could not question local realism. That was his blind spot. That was the assumption he could not see past. And because he could not see past it, he spent the last 30 years of his life fighting against a theory that was actually correct. There is a lesson here, a lesson about physics, a lesson about thinking, a lesson about what it means to understand the universe. The universe is not obligated to make sense to us. The universe is not obligated to match our intuitions. The universe is what it is. Our intuitions evolved to help us survive on the African savanna, to dodge lions and find fruit and attract mates. They did not evolve to understand quantum entanglement. When Einstein said quantum mechanics was incomplete, he was expressing a preference. He was saying, I prefer a universe that behaves in a certain way. And the universe said, I do not care what you prefer. Let me tell you what the experiments actually showed, because it is stranger than Einstein feared. It is stranger than anyone imagined. When you measure the spin of the left particle, something happens to the right particle, not a signal, not a communication, not any kind of influence that travels through space. Something weirder. The two particles are not really two particles. They are one system, one quantum object that happens to have two parts separated in space. When you measure one part, you are measuring the whole system. The whole system responds. The whole system updates. Distance does not matter. It does not matter if the particles are 1 meter apart or 1 million kilometers apart. The correlation is the same. The violation of Bell's inequality is the same. Space, the thing that seems so obviously real, so obviously important, does not matter at all to entangled particles. This is what Einstein could not accept. This is what he called nonsense. This is what he dismissed as spooky. But spooky is just a word we use when we do not understand something. Children find magnets spooky. Medieval peasants found eclipses spooky. Einstein found entanglement spooky. It does not mean the phenomenon is wrong. It means our intuition has not caught up. I want to tell you what I think went wrong with Einstein's thinking, not because I want to criticize him. He was a greater physicist than I will ever be, but because his mistake is instructive. His mistake teaches us something about how to think about nature. Einstein believed that physics should be visualizable. He believed that behind every equation there should be a picture, a story you can tell in ordinary words, a model you can build with your hands. For relativity, this worked beautifully. Curved space-time, falling elevators, trains and lightning bolts. Einstein could explain his theories with images and thought experiments that anyone could follow. He expected quantum mechanics to be the same. He expected that beneath the strange mathematics there was a sensible picture, a hidden layer where particles had definite positions and definite velocities, and everything behaved like a tiny billiard ball. But there is no such picture. Quantum mechanics does not allow it. The mathematics is not describing a hidden layer of billiard balls. The mathematics is describing something new, something that has no analogy in everyday experience, something that cannot be visualized because it is not like anything we have ever seen. This is hard to accept. It was hard for Einstein to accept. It is hard for me to accept. But accepting it is the first step toward understanding. The universe is not required to be a story. The universe is not required to make a picture. The universe is required to obey the equations. And the equations say that entanglement is real, local realism is false, and Einstein was wrong. Now here is what fascinates me most about this whole episode. Einstein was wrong about the EPR argument. The experiments proved him wrong. Bell's inequality is violated. Quantum mechanics is correct. Case closed. But Einstein's paper was still one of the most important papers ever written about quantum mechanics, not because it was right, because it was wrong in such a productive way. Before Einstein's paper, physicists accepted quantum mechanics without thinking hard about what it meant. The equations worked. The predictions matched experiments. Why worry about interpretation? Why waste time on philosophy? Einstein forced them to worry. Einstein forced them to think. His paper crystallized the issues. It sharpened the questions. It made explicit the assumptions that everyone had been making without knowing it. And John Bell's great achievement, the achievement that finally settled the debate, would never have happened without Einstein's wrong paper to inspire it. Bell read the EPR argument. Bell took it seriously. Bell found a way to test it. And in testing it, Bell revealed something deep and true about the nature of reality. Wrong ideas lead to right discoveries. Bad questions lead to good answers. Einstein was wrong, but his wrongness pushed physics forward in ways that being right never could have. I still remember reading that paper for the first time. I remember thinking, this is clever, this is elegant, this is exactly the kind of argument that would convince me if I did not already know how quantum mechanics works. But I did know how quantum mechanics works. I had calculated with it. I had used it to make predictions. I had seen those predictions confirmed in experiment after experiment. And I knew that whatever Einstein was arguing, the universe had already voted. Einstein wanted a universe where things exist, whether or not you look at them. The universe said no. Einstein wanted a universe where influences travel no faster than light. The universe said no. Einstein wanted a universe that makes sense in ordinary terms. The universe said no. The universe does not care what we want. The universe does what it does. Our job is not to tell it what is reasonable. Our job is to observe, to calculate, to test, to discover. Einstein taught me that. He taught me to question assumptions. He taught me to follow logic wherever it leads. He taught me that even the most obvious beliefs might be wrong. And then he forgot his own lesson. He assumed local realism was too obvious to question. He built an argument on that assumption, and the universe proved him wrong. There is no shame in being wrong. There is shame in refusing to learn. Einstein refused to learn. He went to his grave believing that quantum mechanics was incomplete. He never accepted the experimental evidence. He never updated his beliefs. That is the tragedy, not that he made a mistake. Everyone makes mistakes. The tragedy is that he could not let go of a beautiful intuition that happened to be false. The moon exists when no one is looking. That is what Einstein believed. Maybe it does. Maybe it does not. But the electron does not. The electron is not anywhere until you measure it. The spin is not up or down until you check. Reality at the quantum level is not a thing that exists. Reality is a thing that happens, a thing that emerges, a thing that is created in the act of observation. This is what Einstein called nonsense. This is what the universe calls truth.